So we start with a problem, and that problem is, how do you find the slope of a tangent to a curve? So here's just some random curve, y equals function x. I'll pick a point P here. There's the line, I'm calling it the line K. What would the slope of that line be, basically? Now, normally we'd say, well, slope of the line, no worries. If I've got 2 points, y2 minus y1 over x2 minus x1. But when I'm talking about a tangent, I've only got 1 point. So how do I find it? What I could do is I could pick another point on the curve. Now, the slope of PQ would be an estimate for the slope of the line K. Yeah, admittedly, with this diagram, it'd be a terrible estimate. But of course, where could I put Q to get the best possible estimate? Where? As close to as possible. So that actually there was no gap between the two. So theoretically, they are in fact the same point. But if you can imagine the points touching, so that, no. And this is where the idea of limits is going to come in handy, because I'm going to say I want the difference in the x values to be approaching 0. So actually there is no difference, though they're basically the same point. So as close to P as possible would give us our best estimate. So right, let's just magnify that up a bit. So there's P and there's Q. The coordinates of P will be x and then whatever function x when we substitute it in. Q will be x plus some amount. I've moved along a bit. And remember, we want that h to be as small as possible, close to 0 as possible. The function value then, the y value, would be whatever we get when we substitute in x plus h into the curve. So our slope would be function x plus h minus function x over x plus h minus x, which just leaves us with h on the bottom. And there's our problem. If we make it equal to 0, we end up with 0 on the bottom of the fraction. This is where our idea about limits is going to make life a bit easier. So the exact value of the slope of k, we need to calculate the limit as h is approaching 0. So our actual slope, and there will no longer be an approximation, this will be exact. It will be the limit as h approaches 0 of function x plus h minus function x over h. That's the derivative. Right? That's what we call the derivative of y with respect to x. How does y change as x changes is basically what that means. A derivative is a measure of change. So how does y change as x changes? Different symbols. Probably the most common we see is dy dx. The d probably evolves from the Greek letter delta, and delta is often used in science and maths to represent change. So that's probably where the d came from, I would imagine. Sometimes it's y with a dash or a prime, some people call it, but an apostrophe, I suppose some people even call it. The y dash is a way of saying the first derivative. Sometimes it's f dash x. Right? So the original function is function x, the derivative is f dash x. Sometimes we simply say, well, I'm going to differentiate whatever the function is with respect to x. So they actually write out the whole function in there rather than saying y. Okay. So as I say, derivatives are measure the rate of something changing. And this is why it's so useful, because when we want to investigate things that are happening in the real world, change is happening all the time. I mean, a lot of science involves measuring change. So all right, our derivative, it's the same formula, but I'm no longer calling it the slope of the tangent. It's the slope of the tangent when we're looking at that one specific example of finding the slope of a tangent of a curve, but the derivative can be used for much more things than just that. Anytime there's a change between the two variables. So this formula, if they ever ask you to differentiate from first principles, there's the formula we use. It's called first principles because I guess it's the first idea that we've learned about in what we call calculus. It's okay, differentiate y equals 6x plus 1. Now, we should know the answer to this if you remember what we said the derivative measures. Derivative measures the slope. We know the slope of this line. So we should get an answer of 6. Let's see how we go. Well, function x will be 6x plus 1. Function x plus h, whatever I see in x, replace it with x plus h, will be 6x plus 6h plus 1. So subbing it into our formula, the limit as h approaches 0. The top, we get a bit of cancelling happening, and I'm left with 6h over h, factorise. Well, in this case, I don't need to factorise. It's already one term, but factorise and cancel, that's the technique we'll use. And I'm left with 6. Well, as h approaches 0, well, 6 is constant. Doesn't matter what h is approaching. It's always going to be 6. And fair enough, because our straight line, it doesn't matter what value we're talking about. That slope is always going to be 6. So there's our first principles. A parabola is more interesting, of course, because as we move around the curve, the slope changes. So let's try this one, x squared minus 5x plus 2. In fact, we're going to find the equation of the tangent. But in order to find the equation of a tangent, I need the point, I need the slope. I've got the point. We'll need to use our calculus to find the slope. So function x will be x squared minus 5x plus 2. Function x plus h, well, let's expand that whole thing out. There it is. X squared plus 2xh plus h squared minus 5x minus 5h plus 2. Let's put it into the formula. And again, we should see some cancelling happening here. Basically, anything that doesn't have an h in it should cancel. So the x squared goes, the 5x goes, the 2 goes. So that way I now can factorise and cancel and get rid of that h off the bottom of the fraction. And so I'm left with 2x plus h minus 5. So as h approaches 0, that'll be 2x minus 5. Now that is not the slope. That is the formula that will allow us to find the slope. Because notice there's an x. We substitute in the x value and then we'll find the exact slope at that point. So for our question, it's when x equals 1. The derivative turns out to be negative 3. So we know the slope is negative 3. Put it into the point slope formula. And y equals minus 3x plus 1 would be the equation of the tangent at that particular point. But of course, it's useful because sometimes we don't really need to know the actual number. Sometimes we're more interested about, hey, where does the graph turn? If you think about the vertex of a parabola, or any shape really, that's going up and down, what's the slope at the point where it turns? 0. So simply finding the derivative equals 0 can solve a lot of problems. When we want to find maximum and minimums, another problem that happens a lot. I want to find the maximum volume of something, or minimum amount of area of paper I need to make something. So I don't need to draw up a graph of the relationship of the different sizes. All I need to do is find, well, all I'm interested in is that turning point. When's that derivative equal to 0? That'll be the solution to my problem. And that's the beauty of the calculus, is whilst it is all based on the graphing, we don't necessarily need to draw the graph to solve the problem. Okay, so let's have a go at a few of those. You'll notice in the text, they use different notations for first principles. So number 12 there, just do as h approaches 0. We'll do it our way. It should make sense then.